Greetings everyone. My name is Uber Manor Sheikh and I am a student currently pursuing my BTech degree in Computer Engineering department at MIT Academy of Engineering. Today for our subject Exploratory Data Analytics, I'll be presenting on the topic optimization of loss function and best fit line using gradient descent. Let's get started. So, what's our goal today? We have a few key objectives. First, we'll understand the concept of a best fit line in regression and define the simple regression equation. Next, we'll explain the crucial role of the loss or cost function. Then I will introduce you the powerful gradient descent algorithm. And finally, we'll see exactly how gradient descent helps us find that best fit line by minimizing the loss. To start with, what is linear regression? At its core, linear regression is a statistical technique used to find a linear relationship between two variables. For example, we might want to see the relationship between hours studied, which will be a variable x, and exam score, which will be a variable y. The goal is to find a single straight line that best fits all our data point. This line, which describes the relationship, is represented by a simple equation y equals to mx plus c. You may have studied this equation many times in your life, where y is dependent variable, what you want to predict, which is the exam score here. X is the independent variable, what we use to make the prediction, which is the study hours here. M is the slope of the line. It tells us how much y changes for one unit change in x. And C is the intercept. It's the value of y when x is 0. So we need to find a line. But what does best fit actually means? If you look at this slide, you can see a scatter plot of data points. For any set of points, we can draw an infinite number of possible lines. Look at these three graphs given below. The line on the left, it's a pretty bad fit. The line on the far right, it's also a bad fit, but the line in the middle, that one which looks really good, it seems to be the closest to all the data points combined. The best fit line is a single unique line that best represents the underlying relationship in our data. But to look good isn't very scientific and specific. We need a find, we need a way to measure which line is best. And that brings us to the problem. How do we quantify? How do we measure the best? We do it by measuring how wrong our line is for each data point. This wrongness is the error, or what we call loss. As you can see in this image, the error is the vertical distance from actual data points down to the prediction line. We call this the residual. So the best fit line is simply the one line that has the smallest total error when we add up errors for all the points. This is where the loss function comes in. A loss function, or also known as the cost function, is just a formula that calculates the total error for a given line. That is, for a specific value of m and c, a very common and effective loss function is the mean square error, or MSE, which you see here. It might look complex, but it's simple. It takes the actual value of y, subtracts subtracts the y value of a line predicted, and squares that difference. It does this for all the n data points, adds them all up, and then find the average. But you may ask, why do we square the error? There are two big reasons. First, it makes all the errors positive. So too high and too low don't cancel out each other. And secondly, it heavily penalizes larger error. A big mistake is much worse than too small. So our goal is to find the slope and the intercept that make this mean square error value as small as possible. That brings us to our main objective. We need to find the specific value of m and c that results in the lowest possible value for a loss function, the mean square error. If you could plot the MSE for every possible slope and intercept, you would get a 3D ball shape like you see in this graph. A base fit line corresponds to the slope and intercept values at the exact bottom of this bowl. Our job is to find that minimum point. So again, how do we find the bottom of the bowl? We could try a bunch of random values for slope and intercept, but that would be incredibly slow and inefficient. We need a smart, efficient algorithm to find the minimum point. That solution is gradient descent. Gradient descent is an optimization algorithm, and its entire job is to find the minimum of a function. The concept behind the gradient descent is actually very intuitive. Suppose an analogy. Imagine you are standing on a hill which is very foggy. This hill is your cost function. You want to get to the valley, the lowest point, but you can't see it because of the fog. What do? You can feel the slope, the gradient under your feet. So you find the direction of the steepest downhill slope and you take one step in that direction. When you stop, you check the slope again. Find the new steepest direction and take another step. You repeat this process, taking small steps downhill until you reach the flat bottom of the valley. That's all gradient descent is. It's an algorithm for walking down a cost function to find the minimum. As you see in this image, the formula uses theta 1. That's just a general mathematical name for a parameter, which in our case is m or c. Let's have a look at the method more formally. First, we start with random values for slope and intercept. This is like dropping ourselves at the random point on that foggy hill. Second, we calculate the gradient. The gradient is the slope of the cost function. It's a vector that tells us two things: which direction is uphill and how steep it is. This vector can be calculated using partial derivatives from calculus. Third, we update slope and intercept. We take a small step in opposite direction of the gradient because the gradient points uphill and we go downhill. You can see the update rules here. We subtract the gradient multiplied by a learning rate. This learning rate is just the size of a step. It's a key value. If it's too small, it will take us forever to get to the bottom, and if it's too large, we will overshoot the bottom and might bounce around forever, never finding it. Finally, we repeat step 2 and 3 many times until the loss stops decreasing. This tells us we have reached the bottom. This slide shows the whole process perfectly. On the right, you would see the 3D bowl of the cost function. On the left, you see our data points are a regression line. This animation shows epoch 0, which means this is a starting point. Our first random guess. The red line is terrible fit for the data, And you can see on the right, the red dot, which represents our current loss, is very high up on the board. In this animation, you would see the red line on the left moving, getting closer and closer to data points with each step. And at the same time, you would see the red dot on the right walking down the side of the board, getting closer and closer to the minimum. This animation shows how the algorithm learns and improves a line with each iteration. You will see this chart uses W and B. These are just other common names for M, width or slope, and C, intercept. So, to conclude, we use a regression equation y equals to mx plus c to model the relationship in our data. We use a loss function like mean square error to tell us how bad our line is by summing the square errors. Our goal is to minimize this loss by using gradient descent. Gradient descent is the optimization algorithm that does this. It walks down the cost function by taking iterative steps in the downhill direction. By minimizing this loss, gradient descent finds the optimal value for M and C, which gives us a final base rate line. Thank you. That concludes my presentation. If you have any question, you can ask me in the comment section. We will see you next time.